Hi everyone, this is Minal. I'm a postdoctoral fellow in South Korea and I make videos on GPR method for beginners. So if you are new to this GPR method, then this video is going to be very useful for you. In this video, I'm going to discuss about the filtering method of GPR system. So I'm starting a new series on my channel MK Geophysics about filters used in GPR methods. I will cover all the filtering methods, okay? And this will be the first video for filters used in GPR method. So in the initial videos, I'm going to discuss about the basics of filtering method, okay? And I will cover the theory part. Then I'll discuss the application, and at the end of this series, I'll be discussing the advanced filtering theory and its application with some mathematical derivations. So for the initial parts of this filter series will be very helpful for the beginners and as well as the people who are working in the GPR method. And this part is also be useful for the people who works in GPR method or who are researching on GPR method. Okay, so stay tuned for all the parts. So this in today's video, I'm going to discuss about the high pass and the low pass filters, which will be the first part of my filter series. Okay. So filters are basically applied to the data, GPR data you have collected, and what filters does, filter basically improve the quality of image. How it improves the quality of the image? How the filters generally remove background noise or the cultural noise from the data or the instrument noise. So it basically removes the background noise, instrument noise, and the cultural noise. But before discussing the high pass and the low pass filter, I think I should clarify few things so that everyone can understand. The first point I would like to discuss, that is the Fourier transform. So in this discussion, I'll be avoiding mathematical expression as much as I could. Okay, so first one is the Fourier transform, and you are familiar with the Fourier transforms, I think. Okay, so what generally Fourier transform used for? Fourier transform used to convert the time domain signal, that is TD, into the frequency domain signal. So you have time domain waveform and you want to represent that into frequency domain. Okay, then you will be applying Fourier transform. There is another term that is called inverse Fourier transform. As the name suggests, it will convert the frequency domain data or frequency domain signal into time domain signal. Okay, people nowadays in practical or when you are programming or when you are using some programming to do Fourier transform, you generally will be using fast Fourier transform or inverse fast Fourier transform. They do the same, but these methods are faster than the normal Fourier transform or the regular Fourier transform. So if I'm mentioning Fourier transform, that means I'm mentioning the first Fourier transform. But for now, forget about the first Fourier transform or the inverse first Fourier transform. Let's consider that I'm talking about the Fourier transform. Now, why I'm talking about this? This will help you to understand the filter part I'll be discussing in today's this video or in the upcoming videos. So I think I need to clarify a few things with you guys. Okay. Now, in case of Fourier transform, what happens? Okay. Let me give you an example. Suppose you have a triangular waveform like this. Okay, this is in the time domain, this is t, okay, and this is in time domain, and if you convert this into the frequency domain, it will be looking like this. Is very important to understand why, because later when I will be switching from time domain to frequency domain, I'll you shouldn't be feeling like that you are not understanding anything. That's why I'm discussing this part as a background of the filtering method. Okay, so this is the time domain. If time domain signal looks like this, okay, in a triangular waveform, let's say, in the frequency domain it will be looking like this, and you are familiar with this type of curve. This is called the bell curve. Okay, so time domain triangular waveform converted into bell curve in frequency domain. Now, what will happen if you have a square wave? So let me draw a square wave, and it will give you a square wave of amplitude A. So this is in time domain t. So let's say minus tau by 2 to plus tau by 2. Okay, that's the extension. And if I define this small x t equals to A when minus tau by 2 less than equals to t less than equals to plus tau by 2. Okay, that's the limit. It's easy, and it's 0 when rest of the cases, rest of the limit, rest of the cases it will be 0. If you convert this into the frequency domain, it will give you something like this, where the amplitude will be diminishing. I'm not drawing it properly. Okay, and the sin cx function, and in the frequency domain this can be written as x f equals to a t, a tau. So this can be written as xf equals to a tau sin c pi f tau. Tau means the range, the duration of the pulse. That's the duration of the pulse. So if you are having a square wave in the time domain, it can be looking like a sin c function in the frequency domain. Similarly, if you have triangular wave in the time domain, then it will be a bell curve in the frequency domain. Another thing I would like to clarify so that you can understand this filtering method more efficiently involves the basic principle of the GPR method. Okay, so what GPR basic principle tells us that in GPR system there is a transmitter, there is a receiver. Transmitter transmits impulses, and receiver, in my previous videos I have mentioned this several times, that transmitter sending the impulses to the ground, and it gets reflected from the layers or the dielectric layers boundary of two different layers. Okay, and that reflected signal will be received at the receiver, and everything will be controlled by the control unit. So receiver, this receives signal. Clear? Now let me discuss about, I have said the impulses. What do you mean by the impulses? Okay. Now to discuss the impulse, let me tell you an example. If you are having trouble to visualize impulse, let's take an example of our real life, like you have a flashlight like this. Okay, that's the flashlight or the torchlight, whatever you want to say, and there is a switch here, and you are playing with the torchlight, you are giving some kind of signal, you are sending some kind of signal by putting this on, and at the next instance you are putting that off. If your time is, the time you are keeping this on or the time you are keeping this off is very negligible, then you can say, so this is not directly anywhere, anyway it's not related to the GPR or the GPR method, but this is the example I'm giving you to visualize the what impulses mean. So when you are putting this on and off, okay, without taking any time or keeping this on for a large time or keeping this off for a large time, that means you are sending an impulse from point A to from point B. So the person standing here at B, he or she will be looking at that light, okay, and he or she will be seeing the blinking of the light, okay, and this is the fundamental concept of the impulse. This is not related to the GPR basic principle, but similar kind of things we do for the GPR in a more sophisticated way. But before discussing the practical part, what we desire in case of GPR, uh, impulse GPR, what we desire, we basically desire to send signal which has the pulse width, let's say equals to 0 or near about 0. That's our objective. And suppose, so this is the time you are sending the pulse and it's showing the amplitude, then again it's off, then again on, then it's off, then on. This is the pulses you are sending, that's you desire, and this function is called Dirac delta function. But the problem with this, why we are not using this, is that as you can see the pulse width is 0. First, it's very difficult to achieve this theoretically. Second problem is that the attenuation, it will not penetrate even the first layer. So we have to design something, okay. From this point they thought that let's design something which will uh, radiate or which will transmit the pulses with less width, okay. So if you are not having an idea what I mean by pulse width, then let me give you an example. Suppose I'm taking a random pulse. This side I'm plotting amplitude, this side it's time. Okay. Okay. So it will be diminishing. Okay. And this will be your pulse width delta t in time domain. This is t. So in time domain, this will be your pulse width. This is called pulse width. So what they are trying to do, that instrument designer, they are trying to design the instrument so that delta t near about 0. For this reason, okay, for this reason, they have designed the GPR pulse of the or the transmitting pulse like this. So where this could be the pulse width from here to here, this is the pulse width. This here, the peak at this point, this is called the sorry, this is the delta t, this is the time t, okay, and this portion is called delta t, and this is in time domain. You are plotting amplitude with time and you are having this one. So this will be more like condensed, and this the pulse will be looking like this. This curve is in time domain as I discussed. Suppose this curve is of 100 megahertz GPR antenna. Okay. Now if I convert this waveform into the frequency domain, then you can see that it is giving you the bell-shaped curve, okay, where there is a peak, and this peak will be termed as FC. What is FC? FC is the center frequency, which will be equals to 100 megahertz. But in practical, it will be plus minus 10 nanosecond. Okay, that means it will be plus minus. This is if you want to replace the time with frequency, it will give you 10 to the power 8 hertz. So far, I have discussed or I have explained how the waveforms are looked like in the time domain or in the frequency domain. Now I'll be discussing another thing in this regard, or based on this GPR basic principle, is that you know that the transmitter sends short pulses of electromagnetic energy into the ground. The pulses travel, suppose these are the layers, several dielectric layers. This is transmitter, this is receiver. The pulses will travel and it will be reaching to the receiver after reflection or refraction. Okay, it's clear to everyone. Now, one statement I like to give you, that Earth acts like a filter or series of filters. Okay, so this layer will be acting like a filter, this layer will be acting like a filter, this layer will also be acting like a filter. So what will happen if a pulse encounters a change in the material property? What will happen? So what happens, generally a part of the energy reflected back to the surface and rest basically continues to dig deeper. Okay, now as I have mentioned that Earth acts like a filter, think of the subsurface as a series of filters. Each layer, okay, of the material, whether it's soil, rock, voids, it acts as a filter that modifies the GPR pulse. Okay, and these modifications depend on the material properties like the dielectric constant and the conductivity. I think in my previous videos I have already covered that. I'm reminding you again. So depending on the dielectric constant value and the conductivity value, your signal will be constantly modified, and whatever you will be receiving here, that will be a different modified signal. So suppose let's assume that the signal you are sending is small xt, and the property or the average property of the subsurface is ht. Okay, so the signal you received here is yt, can be expressed as yt equals to xt convolved with the HT. This is very simple equation. So whatever the output you are receiving is the product of the pulses you are sending and uh, the filter properties. So it's highly depend on the pulses you are sending and the filter properties. So that will be received at the receiver end. Okay. So when a pulse basically hits a layer, its shape and amplitude changes, and this is changes due to this convolution. I wanted to clarify these points or these topics before discussing the high pass and the low pass filter. Let's talk about the high pass and the low pass filters. After modification by the earth, as earth acts like a filter or like a series of filters, you are having a signal at the receiver end. This is your function yt. Suppose this is the example of 200 megahertz antenna, and I am considering a bell-shaped curve for our convenience. In real life or in real scenario, it will be more undulated like this. Okay, it will be more undulated than this curve. But neglecting that portion, let's consider is a bell shaped. This peak, obviously, let's say 200 megahertz. The most of the signal which are useful, if you can see from the curve, from this and this. So you have to draw a box. Within this box, the signals are useful. These are the useful part of the waveform. Now what I will do, this is in a frequency domain. So what I have to do, I have to remove this portion and this portion. And why I want to remove this part? Why these are not signal, these are noise? So these are basically, if you consider the zone here, this is generally or in this zone, generally you will find some background noise. Background noise. When I say background noise, that means it's the artificial noise or the man-made noise or noise at the site. At the higher frequency level, due to the instrument, because instrument at the higher frequency level for a particular center frequency antenna, it drifts. So this is also a noise developed due to the instrument. Okay, and I do not want to be or I do not want to see this noise on my radiogram. So I have to remove this portion. Okay, if you understand this part, next part will be very easy. Okay, so what I will be doing here, I will be applying some filter. Suppose the center frequency here is 200 megahertz antenna. Center frequency is fc equals to 200 megahertz, and most of the signals are in this portion. So if I want to use only this part to increase the quality of the image, quality of the radiogram, I have to remove this portion and I have to remove this part. Okay, so I'll be applying, suppose this is 50 megahertz, this is somewhat like 500 megahertz. This diagram is not to the scale, so whatever. If I want to remove this portion and this portion, I'll be applying filter at 50 megahertz. I'll be applying such filter which will allow the waveform or the signal after 50 megahertz. This portion it will allow and this portion it will delete. Okay, and So it's passing the high frequency signal. So high frequency signal will be passed through this filter. If I only apply this filter, this will give you only the high pass or high frequencies are greater than 50 megahertz. Okay, that's why this filter will be called as high pass filter. So this is the high pass filter. If you want to suppose this is the 500 megahertz and you don't want this part, what you will be doing? You will be applying a filter at 500 megahertz and it will delete this part, any signal, any frequencies, any component after 500 megahertz. Okay, so it's applying only the lower frequency than 500 megahertz. That's why this filter will be called as low pass filter. At 50 megahertz, you are applying a filter, okay, and this filter is passing or allowing the high frequencies. That's why it's called high pass filter. Okay, so this is a high pass and low pass, and you are applying both the high and low pass filter together. That is called the band pass filter. So in my previous videos, if you have followed me, then you have known that there are several instances I have mentioned that HPIIR, okay, 2Y, HP, FIR, like this, okay. HP means high pass, LP means low pass. In general, GPR data acquisition or the processing, we use the band pass filter, where we define the high pass and the low pass filter. So in case of high pass filter, okay, for 200 megahertz antenna, 200 megahertz monostatic antenna, this is 200 megahertz, this is the FC, okay. The 50 megahertz will be the high pass antenna, sorry, 50 megahertz will be the high pass filter, and 500 megahertz or 600 megahertz will be the low pass filter. It will substantially improve your quality of the image. Now, how this modified frequency after filter will look like, how the waveform will look like. The waveform will look like more like this way. I couldn't draw it properly, maybe. So this is 50, this is 200. If I plot this here, this will be looking like this. Okay, I think you got the idea. So this is 50 and this is 500 and the middle one is 200. So in this video, I have discussed the high pass, low pass and the band pass filter. In the next video, I am going to discuss about the IIR and the FIR filters, which are actually used in GPR.
Thanks for watching. If you have found this video helpful, give it a thumbs up and subscribe for more geophysical insight. Have questions or topics you would like me to cover? Drop them in the comments below.